apply to the H field, H sub z is equal to minus kc squared H sub z. Right? Anyway, we solved this and we ended up with solutions for the z that was e to the minus j beta z on the z and e to the plus, right, plus or minus. We also solved the phi direction. That was a function of z, and that's a function of phi. We had sines and cosines. And phi and cosine and phi. The solution for the rho now is the one that we end up with the Bessel function and first order and first kind and second kind of the Bessel function, right? And then we looked at the solution for the y's. They were all infinite at 0, and we said since the waveguide is uniform all over the inside region, then I don't expect any singularities here, therefore I dropped the y solution. And we kept only the Bessel of the first kind solution. Now, with the coaxial line, the equations are going to be the same until we start applying the boundary conditions. And with a conductor in here, center conductor, there's no justification for eliminating that, because I'm not dealing with the infinity solution anymore. That is out. So I can accept the y solution. And the solution gets too complicated, by the way. You know, it gets to equations that are not easy to solve analytically, and typically are done numerically, right? To find the, if you recall now, without that, we looked at the Bessel function, the j, the j1, j2, and j3, etc. And we looked at the zeros here, and we said these are the f sub c's are determined by the zeros for the modes of the j, or the slopes, if you remember, the derivative of the Bessel function itself. And we found those zeros and found the different modes that can exist. Well, here you have a solution, like I said, that is going to get more complicated. And instead of doing the analytical, there's a numerical solution here, and a curve that was given in Beaux-Arts. That's typically what you find everywhere else. K sub c a versus b over a. It goes a diagram like this. So from that you can find the K sub c that you have, and approximately the formula that is typically used in practice is K sub c is equal to 2 over a plus b. Right? That's the magic formula that we can come up with. So K sub c is, thank you, K sub c is the related to f sub c. So if you write that as omega c square root of mu epsilon, so you can get f sub c in this case, which is the first cutoff for the higher order mode. The dominant mode or the lower order mode will be the TEM. So you have TEM in your coaxial guide up to the f sub c here, where you start to have higher order modes. So F sub C is 1 over, that's already C. And I have a 2 pi, and you have a 2 here. So you have pi times A plus B. The 7 millimeter airline, which is used for in APC7 connectors and type N connectors, if you design, it's usually 7 millimeter. The outer millimeter and 3.04 millimeter. If you work those dimensions here, you will get 50 ohms in air. So that's 3 times 10 to the 8 times 2 divided by pi, 3.14, times A plus B, which is 10 times 10 to the minus 3. So approximately, that's what? 20 gigahertz. The typical number that we see in the literature is 18. Those 7 meter airlines, the claim is that they go up to 18 gigahertz, and that's where, you know, their performance drops by about 3 dB. But the second order mode kicks in around 20, so you work from DC to about 18. The 3.5 millimeter guide, you take, 3.5 millimeter coax line, you take those and divide by 2, right? So you simply multiply that by 2. So it looks like a 36, that's when the high order mode is. Usually those lines are good for about 26 gigahertz, right? You don't want to go to the next, you know, you don't push all the way to the next mode anyway, right? And you stay where the line performance drops, which is usually lower than the frequency, the cutoff frequency of the next order mode. So it's good to keep that formula in the back of your mind. Like I said, it's an approximate formula because the exact solution is too complicated. Okay? General information that is very, very useful. We'll see you on Monday. Do you have any questions before we go?